Hello everyone, welcome back to my channel. You are learning with Dr. Shobha Nikam. In this video, I'll tell you how to design sequence detector using Mealy FSM as well as Moore FSM. So sequence detector is a circuit which detects input sequence, and if input is as per the requirement, if desired sequence will come, if it will get detected, then output of this sequence detector will become 1, otherwise output will remain 0. As this is sequential circuit, so there is one input clock, it detects input sequence, so another input is desired sequence, and it has one output. To design sequence detectors, we need to follow few steps. So very first is we can design it using finite state machines. So we need to draw state diagram first. After drawing state diagram, we need to write state table from the state diagram. Then in state table, we come to know what is my present output, what is my present state, and what my next state will be. From that state table, by using excitation table, you need to identify inputs to flip-flops, and then by putting these values into K-maps, you can find simplified equations, and then based on those equations, you can draw the logic diagram. So this video is not about only how to draw state diagram using Mealy FSM or Moore FSM. In this video, we will start from the state diagram to the implementation of the sequence detector using flip-flops. So here I'll take simple example of 101 sequence detector. I'll implement this sequence detector using Mealy as well as Moore FSM. I have prepared separate video for difference between Mealy and Moore FSM. The link is given in the description box. So very first thing is we need to identify how many states are required to design the sequence detector. So in Mealy FSM, where output depends on present state as well as present input, number of states is equals to length of a sequence. So here length is 3, 1, 0, 1. There are 3 bits. So here number of states are 3 in case of Mealy FSM. Whereas in case of Moore FSM, number of states is equals to n plus 1. That is length of the sequence plus 1. So here we need 4 states. See, in case of Moore FSM, we need more number of states. So we need more flip-flops to implement same circuit using Moore FSM. When we need more flip-flop, we need to connect external power to each and every flip-flop. So power consumption will increase. Also, when number of flip-flops increases, they'll occupy more space on the chip. Applications of sequence detector are in security and encryption. Let's take an example, simple example of your lock, mobile phone's lock. Let's say your lock is 1, 2, 3, 4. So if you will enter 1, 2, 3, 4 in sequence, then only lock will open. Otherwise, lock will remain closed. So sequence of numbers is very important here, and that is why name it sequence detector. It detects in which sequence numbers are coming. Then in data processing for error correction, in communication systems to identify whether correct sequence is coming or not. In control systems at the input side, we use sequence detectors. Now let's start implementation of 101 using Mealy FSM and Moore FSM. So first I'll draw state diagram. So let's draw the state diagram for Mealy FSM. So let's start with state S0. My first state is S0. You can write ABC also, that's fine. So S0 is my first state. What is my first correct bit? 1. So if 1 will come, correct bit will come, then it will go to next state. See, if correct bit will come, then only it will go to next state. So 1 is my correct bit. If 1 will come, it will go to next state. And output is 0. Output will become 1 when it will detect entire sequence. What if 0 will come? My first correct bit is 1. But what if 0 will come? It will remain in same state with output is 0. Now after S1, if 0 will come, 0 is my correct bit. So it will go to next state, state S2. If 0 will come, then it will go to next state because 0 is my correct bit. But what if 1 will come? It will remain in same state and output is 0. At S2, again, there is probability that 0 can come or 1 can come. If 1 will come, 1 is my correct bit. So if 1 will come, it will go to state S1. And now entire sequence has been detected. So output will become 1. Now see, you need to remember, if correct bit will come, it will go to next state. Otherwise, it will either remain in same state or it will go back to previous state. You need to remember here transition to this S1 was when input was 1. So whenever input is 1, then only we can go to S1. It's not like input is 0 and we can jump to S1. No. Here transition was when input was 0. So if any other time, if input is 0, it will go back to S0 or it will go to S2 because to S2 also transition was 0. Now at S2, if correct bit 1 will get received, it will go back to state S1. But what if 0 will come? So if 0 will come here, 0 is not my correct bit. So it will go to state S0. If 0 will come and output is 0. So here up to this point, what value was detected? 1. Up to this point, 1 and this 0. 1, 0 was detected. And then here 1, 1, 0, 1. Complete 1, 0, 1 was detected. So this is my state diagram for Mealy FSM for this 1, 0, 1. Now we need to convert these states into, we need to assign some binary values to these states. So I have 3 states, S0, S1 and S2. So I'll simply allot binary values as 0, 0, 0, 1 and 1, 0. Because we have 3 states, 0, 0, 0, 1 and 1, 0. Binary equivalent of 2 is 1, 0. So 2 bits are sufficient. Now let's draw same sequence detector using Moore FSM. In case of Moore FSM, output depends on present state only. So here I'll draw first state. This is my first state, S0. Sequence is not yet detected. So output for this state is 0. For S0, output is 0. Here also, if correct bit will come, my first correct bit is 1. So if 1 will come, it will go to next state. So my next state is S1. Entire sequence is not yet detected. So output will remain 0. What if 0 will come? So if 0 will come, it will remain in same state. See, in Moore FSM, we write output inside this circle. Whereas here we write output after every input. So here to left hand side of this slash is input and right hand side is output. So here at S1 again, if 0 will come, 0 is my correct bit. So it will go to next state. If 0 will come, it will go to S2 and output is 0. At S1, it is possible that first bit 1 correct bit will come and next again 1 can come. It is possible. So for that, it will remain in same state if input is 1. At S2, at state 2, first bit was 1, next bit was 0, and then if 1 will come, then it will go to next state, that is S3. If 1 will come, and now entire sequence is detected, 1, 0, 1. So output will become 1. Now here you will say, here when input was 1, it went back to S1 because for this state output wasn't fixed. Whereas here it can't go back to S1 because for this state output is 0. but when my entire sequence will get detected, my output must become 1. So it will go to some new state, and that is why we need more number of states. So here at S2, if 1 will come, it will go back, it will go to next state. But what if 0 will come at S2? If 0 will come, so if 0 will come, it will go to state S0. If 0 will come, okay. Then at S3, if 1 will come, at S3 if 1 will come, it will go to this S1. If 1 will come. So see, it can be like this is my first one in the sequence. So my sequence can be 1, 0, 1. See, 1, 0, 1. 1, 0, 1. Or it is like this is my first one. So 1, 0, 1. So here entire sequence will get detected. Here if it is 0 at S3, if bit is 0, it will go to S2. So this is my state diagram for Moore FSM, for 101 sequence detector. Now let's assign binary values. So we have 4 states, S0, S1, S2 and S3. So 2 bits are sufficient. In case of 5 states, we need to use 3 bits. So here I'll assign value 0, 0, 0, 1, 1, 0 and 1, 1. Now, based on these 2 state diagrams, now let's design circuit for this Mealy FSM and Moore FSM. Let's start with Mealy FSM. And we can use any flip-flop for design of sequence detectors. But here I'll take example of JK flip-flop. Here we have present state, we know inputs, we know next state and we know output. So from this diagram, we will write this state table. We have present states QB, QA. These are present states. Then we have input X, next state QB plus 1, QA plus 1 and output. So I'll write truth table. Simply I have 3 variables. So here I'll write 4 times 1, zeros, 4 times 1, 0, 0, 1, 1, 0, 0, 1, 1. 0, 1, 0, 1, 0, 1, 0. Simple truth table for 3 variables. Now, this is my present state. So, when my present state is 0, 0, S0 is 0, 0. So, here I'll write this is my 0, 0. I'll use different pen. 0, 0, 0, 1 and 1, 0. So, when my present state is 0, 0 and input is 0. Present state 0, 0, input is 0. Then what is my next state? It will remain in same state. So next state is also 0, 0 and my output is 0. Then if my present state is 0, 0 again, my present state is 0, 0 and my input is 1. When my input was 1, next state was S1 and S1 is nothing but 0, 1 but still output is 0. Then if my present state is 0, 1 and input is 0. Present state is 0, 1, S1. Input is 0. Then next state is 1, 0. So next state is 1, 0 and output is 0. Present state is 0, 1 and input is 1. Then next state is again same 0, 1 and output is 0. If my present state is 1, 0, see this is my present state 1, 0 and if input is 0, for this present state, if input is 0, next state is 0, 0 and output is 0. But in case of 1, 0, if my input is 1, then next state is 0, 1 and my output is now 1. And we don't have 1, 1 state. So next state is don't care. Outputs are also don't care. So now these are my present states, these are my next states, this is my output, this is my input. To design circuit using JK flip-flop, we need to know excitation table of JK flip-flop. So for JK flip-flop, Excitation table is nothing but when we know what my present output is, what my expected output is, and based on that we calculate the values of inputs. So here 0 0 1 1, simple truth table 0 1 0 1. Excitation table for JK flip-flop is, it is 0 1 don't care, and here it is exactly opposite. You need to start with don't care 1 0. So this is excitation table for JK flip-flop. Now based on this present and these next states, let's identify the inputs. So inputs are JB, KB and JA, KA, because we have two flip-flops. To calculate JB, KB, we need to compare QB with QB plus 1. So here present state is 0, next state is also 0. For 0 0, J is 0 and K is don't care. So 0 don't care. 0 0 0 don't care. 0 1. For 0 1 it is 1 don't care. For 0 0, 0 don't care. For 1 0, don't care 1. Again for 1 0, don't care 1, and here we don't have 1 don't care. So here we'll write don't care, don't care, don't care, don't care. Then for JA, KA, we'll compare QA with QA plus. For 0 0, 0 don't care. 0 1, 1 don't care. So our table is ready. State diagram done. State table done. Excitation table done. Next step is K map. So we need to draw 4 K maps. One for JB, KB, JA, K. And how many variables we have? We have 3 variables, QB, QA and X. So number of cells in K map are 8. 2 raised to 3 is 8. So I'll start with JB. And here QB, QA, X, gray code 0 0, 0 1, 1 1, 1 0, and here 0 and 1. See, 0 0 0 is 0, 0 0 1 is 1, 0 1 1 is 3, 0 1 0 is 2, 1 0 0 is 4, 1 0 1 is 5, 1 1 is 7, 1 1 0 is 6. So sequence is always like 0, 1, 2, 3, 4, 5 and then 6 and 7. Now let's put values for JB. We'll start with JB. So JB here is 0, 0, 1, 0. 0, 0, 1, 0. And then all remaining are don't cares. So what we can do here for JB equation is we can make pair of 1 and don't care. So equation can be written as, here value of QA is 1. So QA as it is, and what is value of X? X is 0. So X bar. This is equation for JB. Now let's find out equations for KB, JA and KA. Let's put values for KB. KB first. So 4 times don't care. And then 1 1 don't care, 1 1 don't care, JA is 0 1 don't care, 0 1 don't care, and then again 0 1 don't care, 0 1 don't care. For KA don't care, 1 and then 0, and remaining 4 are don't cares. Now let's find out the equations. We need to make groups of more and more number of ones. So I'll make group of all of them. And here equation for KB will become KB is equals to 1 because we have grouped all of them together. For these two ones, I'll make one chord. And for this chord, equation is JA is equals to, Here, what is common in these two? QA is 0 and 1. No. And here it is X. For KA, here what I'll do? I'll make group of overlapping ones. So here I'll fold my K map. So these two and these two will get overlapped. And in case of don't care, you can consider them as 1 or 0. So again here equation will become QA is not same X. So KA is equals to X bar. Now we have equations for JA, KA, JB, KB. We need to find out equation for Y. For this Y. Y is all zeros, 5 times 0. So 0, 0, 0, 0, 0. Then 1 and don't care. So here we can make a pair. And here equation for this pair is, so output Y is equals to QB into X. So this is equation for Y. Let's draw the final circuit. We need to take two JK flip-flops. These two are my JK flip-flops. Equation for JA is X. So input X, which is my external pattern, is directly given to JA. KA is X bar. So I will simply connect inverter here, and through this inverter KA is connected. Then JB. Okay, we'll write for KB first. So KB is connected to 1 or VCC. This is synchronous circuit. So single external clock is connected to both the flip-flops. So single external clock to both of them. Now next is my JB. So for JB, equation is QA into X bar. So I need to use AND gate because there is multiplication. So I'll use one AND gate here. And inputs to AND gate are QA and next is X bar. So this is JB, KB. And then next is output Y. So for Y, the equation is QB into X. So here I'll use one more AND gate. Here I'll get final output Y and another input here is X. So this is my circuit implementation of 101 sequence detector using Mealy FSM. So if you will implement this circuit using hardware, or if you will simulate this circuit, and here when you will apply some sequence and let's say 101 will come. So here when 101 will come in sequence, your output will become 1 after detecting entire sequence. Now let's see how to implement same circuit using Moore FSM. We already have state diagram for Moore FSM and we need to follow same steps. For Moore FSM, we'll follow same state. So this is my present state. This is my input and I'll identify now next state based on this state diagram. So same steps I'll follow. When present state is 0, 0, so S0 is 0, 0. And if input is 0, next state is also 0, 0 and output is also 0. And if input is 1, next state is 0, 1. Similarly, I'll complete this table. Again, by using excitation table, what I'll do, I'll compare this QB with QB plus 1 and then I'll identify the values of JB, KB. So this is excitation table of JK flip-flops. So I'll compare this QB with QB plus 1 and QA with QA plus 1 and I'll identify JB, KB, JA, KA. So this is for JB, KB. Now let's do it for JA, KA. So for 0, 0, 0 don't care. For 0, 1, 1 don't care. I'm doing it by using this excitation table. Now let's put these values into K-map and let's identify equations for JB, KB, JA, KA. Now let's put values for JB, KB, JA, KA. So here 0, 0, 1, 0. 0, 0, 1, 0 and 4 are don't cares. For KB, upper 4 are don't cares and lower are 1, 0, 0, 1, 1, 0, 0, 1. For JA, 0, 1, don't care, don't care. 0, 1, don't care, don't care. For KA, don't care, 1, 0. Don't care, 1, 0. Now let's make groups and find out the equations. So here equation for JB is QA X bar. Here equation for KB is QA bar X bar plus QA into X. So this is like A bar, B bar plus AB. So this is nothing but QA X NOR with X. X is our input. For JA, I have made one chord and equation becomes X. Here only X is common, QA is 0 and 1. Here overlapping group and here X is same and value of X is 0, so X bar. Similarly, now we need to draw K-map for Y. So here Y is 6 times 0, 0, 0, 0, 0, 0, 0 and then it is 1, 1. So we can make pair and here equation will become Y is equals to, this is our output, QB into QA. Now let's implement this. Let's take two JK flip-flops. Here single external clock will connect both flip-flops because this is synchronous circuit. Okay, equation for JA is, see, equation for JA is X and KA is X bar. So JA is X and KA is X bar. So I'll simply connect one inverter here and this is my KA. For JB it is QA into X bar. QA into X bar. So I'll use one AND gate here. One input is QA and another input is X bar. For KB, it is QA XNOR X. So here I'll use XNOR gate. For KB, we need to take one XNOR gate. XNOR. And inputs to XNOR are QA and X. So here one input is X, another input is QA. So this is my input to KB. Now my output Y. Y is QA into QB. So I'll simply use one AND gate here. And output of this AND gate is my actual output Y. And inputs are QB and QA. So this is my circuit. So this is implementation of 101 sequence detector using Moore FSM and this is using Mealy FSM. So this is all about sequence detector implementation. Thank you so much for watching and don't forget to share it with your friends and subscribe to my channel. Thank you.